So any doubts from last class? Otherwise, maybe start writing what we did in the last class. Okay, so let me just recap from what we did in the last class. So what we were interested in was we started looking at this two first order coupled differential equation whose general form is this. And in fact, we were looking at a specific example of what I described as a predator-prey equation. And these were the set of equations where the variables are y and z. And for the predator-prey equation, the idea was that first thing that we wanted to find out was what was the fixed points of the steady state. In fact, for this predator-prey model, we just have, for finding the steady state, you just set the right-hand side to 0, and the corresponding fixed points just turns out to be, so this is one fixed point. And the other fixed point was that this was y was 1 and z was 1. And the question we were interested in was that we wanted to analyze that what is the stability of these fixed points. That means if you are deviating slightly from these fixed points, how does the solution come back to the original fixed point, or does it go away? That was the question we were interested in. And so the generically, if you look at a second order differential equation, this would be the structure and ordinary differential equation. And then what we argued was that just like following the footsteps of what we did for the first order differential equation, we saw that the equations of the fluctuations that we arrived at by Taylor expanding had this general form. So you have ddt of delta y is f prime of y times delta y plus f prime z times delta z, where of course f prime, y prime, etc. are just the shorthand for the partial derivative of f with respect to y evaluated at the steady state, and so on and so forth. So similarly, f prime z is equal to, right? So this was the understanding. And once we have written that, you can immediately see that the general form of this equation is, one second. So it had this particular form, and if we recast this, delta y and delta z are basically the fluctuations of the points from their, steady state configurations. So delta y is nothing but whatever is the y minus the y steady state. Similarly, delta z is nothing but z minus the z steady state, and we are really looking at the time evolution of these fluctuations. And this has this nice form which you can cast it in this kind of matrix form. So this I have just written this. So we call this the Jacobian matrix, and basically this square matrix, the elements of this square matrix comprises of this partial derivatives of this f and g with respect to y and z respectively. So this was the form of the matrix. In fact, if we do this exercise, we can, of course, for the predator prey model, we can immediately easily we know the steady state values of y and z, and we can find out what these the form of these equations are. I mean, the form of this f prime y and g prime y, etc. are, and this had this particular form for the specific case of predator prey model. Next, we in the last class, what we actually argued was more on geometrically, intuitively, that what was the nature of the fixed point. We said that if you are, for instance, for the predator prey model, the fixed point corresponding to 0, 0 is unstable because the fluctuations we could see grows with time. But now what we are going to deal with is how do you generally tackle this kind of problem. So this is the general form. So notice first of all, I want to impress. I showed it two, but imagine that. So this I'll just quickly go through. So suppose you had this equation dy dt is equal to f. Let's say I have three variables in this case. Let's say my variables are f, z, and s. So then dz dt, let's say some function g, y, z, s. And finally, I have, let's say, g, I'll give it some other name, maybe h. So this would be the form of, if I had constructed, again the equations, again I linearize this equation following the similar prescription that we have described. The kind of equation again you would have landed up with for the fluctuations would have been ddt of, in this case the variables are delta y, delta z, and delta s. And again I would have this kind of Jacobian matrix multiplied by delta y, delta z, delta s. And all these elements here, just like I had previously f prime of y, here I have the first row would be f prime of y, f prime with respect to z, f prime with respect to S. Second row would be G prime with respect to Y, G prime with respect to Z, G prime with respect to S. And finally, I have this function H. So this would be the corresponding Jacobian matrix for this. And you can easily convince yourself that in principle, if you had n coupled differential equation, the form of the general structure of the equation of the fluctuations, that means the linear fluctuations we are looking at, in the neighborhood of those fixed points, they will always have this kind of form where you have ddt of all these fluctuations. We can think of it as vectors, and then you have this Jacobian matrix, which basically comprises all the different partial derivatives with respect to the variables corresponding to here, and then so this would be the general structure, and you should actually try deriving it even for 3 cross 3, that you take a general form, this Taylor expand the right hand side about the steady state, and convince yourself that you will have this this generic form of the equation. But for the time being, just to illustrate, let us go back to this 2 cross 2 thing, and the main point is I want you to focus here. Okay. So I have cast this X here in our language is equivalent to this vector, right? This column. Now, this kind of equation you have already seen that this is a matrix, and now, and this is of course the Jacobian matrix formed by this particular object. The idea here is that, if I want to analyze the behavior of this. Finally, what we are interested in is analyzing whether the fluctuations grow or decay with time, right? Now, if you look at the right-hand side, this is something you have encountered in mathematical methods of physics, but also in the context of classical mechanics. That this is the form of I can think of an eigenvalue equation. So this is the form. So think of it as an eigenvalue equation. So what does this kind of eigenvalue? So suppose I find a vector x, so I can call it whatever x prime, and if I multiply this matrix, then it gives me a constant where lambda is some scalar. So it multiplies by some number times this matrix. So that is the general structure of this kind of eigenvalue equation. Now, if I bring it on the other side, then in general, that means I can write it as lambda times identity matrix times x equals to 0. Right? Now, the only way this equation can be satisfied is either the trivial solution, which is basically that if the vector itself is 0, 0, then that's like a trivial solution. But for any non-trivial solution, the condition for this to be satisfied is that so this is a matrix. J minus lambda times the identity matrix is a matrix, and this matrix is singular. Right? J minus lambda times, this is identity matrix. This has to be is singular. And if this has to be singular, then the way it can be singular is that means the condition for satisfying this eigenvalue equation is that determinant of J minus lambda I, this has to be 0. Okay. This is something anyways, I mean, this is a more a recap of what you have done in MMP. I mean, recall the context in which in classical mechanics, there were at least 2 different contexts in which you encountered some this kind of eigenvalue equation. One when you had to find out this moment of inertia tensor. Whenever the moment of inertia tensor, you had to bring it to the diagonal form to identify the principal axis. Then you made a similar transformation, right? You cast it in this eigenvalue equation, and then those lambdas you found out that those corresponded to those principal moments of inertia. That was one context. Another context in which you had encountered was in context of small oscillation. So, I mean, all these examples of where you wanted to find out the normal modes of vibration when you have this coupled string, and there also you diagonalized it, and in order to identify those, so there the interpretation of the lambda corresponded to this eigenfrequencies which you identified. And then the later step was if you wanted to later on construct the corresponding normal modes or the eigenvectors, then you proceed with this. But this was sort of the first step of the the technology of mathematical methods that you use for solving this problem. Why? Because again, just take a look at the form of what is there. See, you have a form of this kind of stuff, right? ddt of delta x, delta y, and then you have this Jacobian matrix times delta x, delta y, which I am saying this is your ddt of this vector, which I'm identifying as vector x times this. Now you can easily see that once I make a similarity transformation, I can bring it to the diagonal form. And what is the advantage of diagonal form? Because that means these fluctuations, I can think of normal modes, which would be some linear combinations of this delta x, delta y. And for those normal modes, when I have made this transformation, when I have identified this eigenvalue equations, then here it is mixing these modes, right? ddt of delta x is something delta x. You would actually get the form of this delta phi 1, delta phi 2 would be some linear combinations of delta x, delta y. And then you would have this yes, I should rather say that. So once you cast in this form, once you identify the normal modes, you can easily see, once I have the equation in this form where you have ddt of some variable, that is lambda times that variable, then you know what the solution of that differential equation is. It will give you solutions which would be, so the solution for this kind of equation would simply be lambda times t, right? So this would be the solution, whatever, something would be some constant. Now that means basically whether your solutions will grow or decay would depend on this lambda, because if lambda is greater than 0, then those solutions will exponentially grow with time. And if those lambda are less than 0, if it is negative, then because it is because of the exponential nature of the solution, it will decay with time. In other words, that means if you have lambda which are negative, it will you will have a linearly stable solution, because the solutions will decay back. So that's the main key point here, that so finally when we write this equation, your task really for doing linear stability analysis is to find out this eigenvalue equation, and then from there find out what are the values of this lambda. So we'll go through this process. So that's the reason why we are focusing on this lambda, because finally this lambda is going to tell me whether the solution is stable or not. And in fact, the conditions we would revisit those conditions, but essentially, the lambda has to be negative for linear stability. So let us just go back to where we were. So I'll talk in very general terms. Let's say, although of course this Jacobian comprises of f prime z, f prime z, j prime, etc., etc. But let's say this. What about if I have some Jacobian form? Let's say ABC. What would be the form of this form of my determinant? So if this is J, if I look at this this object, that means this condition for non-trivial solution, then it is simply a minus lambda d minus lambda. This is equal to 0. Are there any doubts until here? Please clarify. If you have any doubts or questions, then please clarify. What we have done is so I'll just again recap this steps quickly. So we wrote down the form of the fluctuations in the form of a matrix, and so ddt of some vector is equal to some matrix, and this matrix is this Jacobian matrix multiplied with this. Next step is that we want to go to a basis. We want to look at the eigenvalue equation, which corresponds to this j times x is equal to lambda x. And then we want to find out. So once we have written this, we want to find out the non-trivial solution of this eigenvalue equation. And the non-trivial solution just corresponds to the fact that I have to evaluate the determinant of j minus lambda times I, and that has to be set to 0. I start with the most general choice, that some 2 cross 2 matrix, which happens to be the Jacobian, is this form ABCD. And then this condition just simply means this. So this is the step we have arrived at. Now that I have arrived at this step, you can, of course, easily simplify this equation. And what you would get is, so I'll just write down. So equation 1 from, you will get lambda square minus that's all. Actually, one way of doing it is, you know quadratic equation, you know the solution, so you can find out the value of lambda. But let us actually look at it more carefully. Remember, of course, my J here is this matrix ABCD, which for a given set of differential equation, in principle, you know.
Excuse me, sir.
Yes.
Sir, actually, whatever write on the topmost part of the board is actually not visible on the screen. Only when you pull down the board a little, we get to see.
Oh, sorry. This is better?
Yes, sir. Thank you.
See, yeah. Okay. Okay. So this is the Jacobian matrix. So this ABCD would correspond to, of course, F prime Y, F prime Z, etc. So this is the corresponding, from the eigenvalue. Like I said, we arrive at this condition. Now, in principle, one clever way of doing it is that, if this equation would have been factorized, then I could have written it in lambda minus lambda 1 minus. This is, of course, you recognize it's a quadratic equation. So there would be, two solutions in general. I mean, there can be special case where one is repeated, but in general, it will have 2 solutions. And the form of this thing, if lambda 1 and lambda 2 are the 2 roots, then it should satisfy this, right? So let me name it equation 2. So because it's a quadratic equation, it should be factorized in this particular form. So if I expand it, then what we will get is lambda square minus lambda 1 plus lambda 2 times lambda plus, right? So this is equation 3. If you immediately compare equation 2 and equation 3, then what you immediately see is that means lambda 1 plus lambda 2 is equal to, has to be a plus b, and your product of the roots, that has to be, right? I hope it is just clear. All I have done is some simple algebra. This was my equation. This is a quadratic equation. I just compared the form I get. But if you notice carefully, this was my original matrix was this J tilde. Right? If you look at this, my sum of the eigenvalues, lambda 1 and lambda 2, is nothing but basically trace of this matrix J. Right? Trace, if you recall again, you just add up all the diagonal elements of the matrix. So that is trace object. And this object, AD minus BC, is nothing but basically okay. Is this clear? And now, what did we just say? That the requirement is for stability is that this equation, that means the lambda both the lambda have to be negative for stability. Why they have to be negative? Because like I told you that finally in terms of the solution of these normal modes, it would have the form of lambda 1 times, let's say these are the two normal modes. You can immediately see. So what should be the condition that I should put for lambda 1 and lambda 2? That both of them have to be negative. If both of them have to be negative, then it puts conditions on even trace of J prime and delta determinant of J. So first of all, if both are negative, that means my trace, so for linear stability, the sum of the roots, because both lambda 1 and lambda 2 are negative, so the sum also will be negative. That means trace of this matrix J, which is nothing but lambda 1 plus lambda 2, this has to be less than 0. Okay. Second condition is that if lambda 1 and lambda 2 both are negative, necessarily positive, or in other words, but we just saw that the product is nothing but basically the determinant of this matrix of J. So that means the condition for stable roots is that determinant of this matrix J prime, which is just the product of the roots, this has to be greater than 0. Okay. Here I should add one more point. If you recognize that, in some sense, when I'm giving this condition lambda 1 and lambda 2, but you can ask this case, and in fact, it should be one of the questions that should come to your mind, that if you have a quadratic equation, in general, depending on, whether b square is greater than 4ac, in principle, you can have situation where you have complex roots, right? So the roots that you get for quadratic equation, it need not necessarily always be real roots. You can have a situation where your lambda and lambda 1 and lambda 2 are basically complex conjugate of each other. And in that case, what would be the corresponding stability condition? So the answer is rather easy to see that, finally at the end of the day, what would be the form of the solution? It would be e to the power of, lambda t. If lambda is complex, it would be of the form sum, a plus ib times t. That means e to the power of e to the at, e to the power of ib. This part is just oscillatory, right? I mean, this will not face any problem. So that means the stability would be determined whether the real part of lambda, whether that is negative or not. If the real part of lambda is positive, then again it would be unstable. If you look at how this instability will grow, it will basically, grow. It would be, if I look at the oscillations about, let's say this is the fixed point, they will basically grow with that. On the other hand, if the real part of the eigenvalue is negative, then you start with some, it will basically oscillatory damped kind of nature. Yeah? So the bottom line is that condition for stability is that real part of all the lambdas. You must remember, it is important that even if one of the lambda is positive, or if the real part is positive, then you will have unstable situation. So then your steady state would no longer be a stable steady state. So the condition for stable steady state is the real part of the eigenvalues, for all the eigenvalues, that has to be less than 0. For linear state. Now that we have this thing, we can actually revisit the example of this predator prey. What would be the nature of the eigenvalue and what would be the nature of the stability? So, for instance, for the predator prey, one of the steady state which we argued was unstable was this particular steady state. So this was the corresponding the J matrix, right? The Jacobian. So for this particular steady state, what is my J matrix? I just substitute Z is equal to 0. So this is 1, Y is equal to 0. So this is minus 1. And then I have, sorry, so this is 0. Right? For this particular steady state, this would be the corresponding Jacobian. You can immediately see that this particular steady state is unstable, linearly unstable. Why? Because the condition is that the determinant of J has to be greater than 0 for linear stability. What you find here is that if you find out the determinant is minus 1, and so which immediately tells you that this particular steady state in this case will be unstable. So this fixed point, 0, 0 fixed point is unstable. What about the other fixed point? That means the other fixed point which we had was, sorry, this was 1. In this case, if I again look at here, so then this matrix is, this is 0. This is again 0. Here you see, if I take the product of this eigenvalue, then first condition is that the trace is actually 0. So it's not less than. So that's why what we had seen was that it was actually oscillatory solution. And similarly, if you actually look at the determinant, so the determinant of this matrix, this is again positive. So you can see it. So this could be plus 1. So the determinant is positive, but the trace of this matrix is 0. So we do not have a situation which is which is actually marginally. In fact, in this particular case, you can easily work out what the, because remember, so finally the determinant that has to be 0 is, that means this is your J matrix. So if I had 0, so that means 0 minus lambda, this is minus 1, and this is plus 1, and this is again 0 minus lambda. So this has to be equal to 0, which actually gives you lambda square plus 1 is equal to 0. This would be the corresponding eigenvalue, and so basically lambda is plus minus I. So that give you that, we were yesterday discussing that you get to see an oscillatory solution, because the corresponding how this fluctuations will grow, this would go as, that means e to the power of, and since you have got plus minus I, So that's why we were getting all this, solutions of the fluctuations which were going around in circle. So this is sort of how you use the linear stability analysis. I am just going to point out what would happen when you go to higher dimensions. Notice that for second order, meaning for two differential equations, what you land up with is a quadratic equation in principle. If you, for instance, had three coupled differential equations, so then what you would land up would be a cubic differential equation. Principles again remain the same. For cubic equations, there are these two cases where one for which all the three eigenvalues are real, and again, so in that case, what you have to see is that all these three eigenvalues have to be negative for a stable, linearly stable solution. And the other case where you have one real and two complex conjugate. For the complex conjugate, you have to look at the real part, whether it is negative or not, and for the other real part, and that's going to tell you whether it is linearly stable or not. Next is what I want to emphasize is that look, all this analysis that we have done is in the neighborhood of a fixed point. So we have essentially linearized the equation. And all this analysis, whether the fixed point is stable or not, is as far as linear stability goes. In real life, what can sometimes happen, and in fact, that is, you can imagine a situation that, so let's say I do a linear stability analysis about some fixed point. Let's say you find out that that particular fixed point is unstable. That means if you start from the neighborhood of that fixed point, at least up to the linearization, you are going away from that fixed point. But if the underlying equation is a nonlinear equation, there can be circumstances where those nonlinear terms will start kicking in. Because finally you might start in the linearly stable regime where your delta y is small, that means that term is small. But if that is unstable, that delta y will keep on growing with time, right? And once it keeps on, all this analysis of linearization and linear stability will break down, and in that case, the actual differential equation, the nonlinear, if it's a nonlinear differential equation, those nonlinear terms might kick in, and sometimes there is this phenomenon where these nonlinear terms are able to stabilize this situation. So this is also called nonlinear stabilization mechanism. So I'm just telling you. I mean, we are not going to discuss in details what are the mechanisms of nonlinear stabilization, but I just want you to at least be aware. And in fact, so today I'll stop here. So tomorrow I'll actually show a very famous equation, nonlinear equation, which is also known in context of chaos. So I would tell a little bit about this equation, and that you should be doing it as a part of your assignment. So I think I'll stop here. If you have some questions, I'll take that. So the main idea that I try to emphasize in this last two lectures is this concept of a linear stability analysis. That how do you analyze that a particular set of coupled differential equation? How do you find out whether the steady states of those equations are stable, linearly stable or not? And what we found down the line was that you have to basically find out the Jacobian, and then we write down that the equation of the fluctuations can be written in the form of an eigenvalue equation. And the trick is to find out the corresponding eigenvalue equations and the solutions or the lambda for that particular eigenvalue equations. The order of that equations involving the eigenvalue lambda would be the same as the number of coupled differential equations. So if there are n, then the order of the differential of the lambda equation would be lambda raised to the power of n. And once you have that, then the condition is that all the real part of the lambda, all the lambda, meaning all the solutions of lambda, they should be negative. And once you have that, you basically know whether a particular steady state or fixed point is stable or unstable. So I'll stop here. If you have any questions, please go ahead. Yeah, is it clear to everyone? Okay, so if it is clear, then we would meet tomorrow, and then I'll stop the recording for today.